Now come to the systems 12. So we use the definitions. What's a divisibility? Suppose A not equal to 0 is an element of a commutative ring R. A is set to divide B. A is set to divide B. B is also an element of a ring R. There exists element C belongs to R. C belongs to R such that B equal to CA. B equal to CA means, suppose I write A divides B. B equal to A into C. C is also S. C, suppose 3 divides 15. 3 divides 15 means 15 can be written as 3 into 5. So 3 and 5 is there. 5, 3 and 15 here. 3 and 15. Z, 5 belongs to Z. 5 belongs to Z. Similarly, 5 belongs to R. R is a ring. In the same case, we can write B is equal to C. A divides B. In simply we can write, in symbolically we can write A divides B. This is a pure concept. What's a divisor? If A non-zero elements, A and B is a non-zero, A divides B, suddenly B can be written as B is equal to CA. CA or C is an element of whatever. Now we come to the next concept. A concept means associated. What meaning of associated? Means A tilde B. Tilde means I want the equality. Means equality A should be something multiple of B. Something multiple of B. In something means a unit elements. Yeah. Suppose A tilde B means A is equal to UB, where U is unit. Where U is a unit. A is equal to 1 into B. That is called. That associated means let R be a commutative ring with unity. The element 1, R be a commutative ring with unit element 1. Then an element A of R is said to be associated B belongs to R. An element A of R is said to associate of B. Associate of B. If A is equal to UB, A is equal to UB for some U in R, for some U in R. In symbolically we can write A tilde B. A tilde B, which read as A is an associate of B. A tilde B simply we can write B equality means A equal to UB, where U is a unit. Simply write. This is called associated. Now we come to the irreducible definitions of irreducibility. What meaning of irreducibility? Suppose if we take capital D is an integral domain. You know the basically integral. What's integral domains? We already know the some previous session. Integral domain with unit element 1. With a unit element 1. A non-zero element, non-unit, non-zero, non-unit. A can be written. A should be not equal to 0 other than 1. A not 0, non-unit. A belongs to integral domain D. Having the only trivial divisor is called prime. Only trivial divisor is called a prime or irreducible of D. Suppose we take a prime elements. What's a prime element? Suppose 5. What's a 5? 1, 5. 1 into 5. 5 can be written as 1 into 5. What's the divisor of 5? 1 and itself. 1 and itself. Yeah. So unit, a non-zero, a non-unit element. Non-zero, non-unit. So 1 cannot be done. 5 divides 5. That's all. It's 5 divides 5. Itself, it's a trivial divisor. 7. What's the 7 can be written as 1 into 7. So 7 is divided. 7 divides 7. This type is called irreducible. Irreducible means let D be an integral domain with a unit element 1. A non-zero, non-unit element A in D having only trivial divisor is called a prime or irreducible of D. Suppose if we take a 15. 15 can be 3 into 5. Yeah. 3 not equals 0, 5 not equals 0. 3 divides 15, 5 divides 15. This is a 3 and 5 is a proper divisor. 3 and 5 is a proper divisor. So this is irreducible is called reducible. Is called is reducible or composite element of D. Is called a composite element of D. So only prime is called irreducible of D. Other than prime is composite is called reducible of D. Irreducible of D. Now in the previous example, divisibility, I take an example of divisibility. What's the divisibility? 3 divided 6. 6 can be written as 3 into 2. But 2 belongs to in R and Z. 2 belongs to Z. However, in the ring of integer, 3 is not the divisor of Z. 3 is not the divisor. So, one more example by using associated. Suddenly, this is called an example of principal ideals. That the only units of integral domain of integers are minus 1, 1. Therefore, if A is any non-zero integer, then it has exactly 2 associated, namely minus 1 of A and 1 into A. Minus 1 of A and 1 into A. That is A and minus A and minus A. Thus, the 2 associated of 5 are minus 5 and 5. Thus, 2 associated of 5 are minus 5 and 5. This is an example of principal ideal. Recall that. By using the principal ideal, we introduce an associated form. So, associate A tilde B means A equal to UB. U is a unit. Using that, in the case of integer time, the only units of integral domain of integers 1, minus 1, 1. The only units of integral domains of integers are minus 1, 1. So minus 1, 1, if A is an element, the multiply minus 1 of A and 1A. Minus 1 of A and 1A. So A and minus A. Thus, 2 associates of A are A and minus A. Suppose if we take 5, what is the association of 5 are minus 5 and plus 5. That's the way. If we come to the one more example, the only units of the domains of a Gaussian integers are only units of domains of a Gaussian integers are 1, minus 1, I, minus I. Yeah. Suppose if we take complex number, what's complex number? A plus IB. A plus IB is any non-zero element of this domain. Then it has exactly 4 association. Namely, so A plus IB is A plus IB. I'm multiplying an element 1. So we get same A plus IB. So minus 1 times of A plus IB is minus A minus IB. Minus A minus IB. Again that I times of A plus IB. So IA plus I square B. What's I square B? So minus B plus IA. One more element associate. So minus I of A plus IB. So yet minus IA minus I square B. What's minus I square B? Plus B. So minus IA. So again this is one also. So here, so this is associations of a Gaussian integer. We are using the Gaussian integer 1 minus 1 I minus I. So if we take that complex number association, 1 times of that we get same, minus 1 times of that we get changes, I times of that we get minus I times of A plus IB we get again that in the same field, in the same complex number. In the integral domain, the integer, again I come to the divisibility conditions. What's a proper or improper divisor? Suppose if we take 6, I'm saying again I come to the reducible with reducible. What are the divisor of 6? There, plus or minus 1 plus or minus 6 is a trivial divisor, simply called improper divisor. Plus or minus 2 plus or minus 3 is called a proper divisor of 6. So like that. So Suppose if you take one more example, if you take 15, 3 into 5. Yeah, plus or minus 1, plus or minus 15 are a trivial divisor. Plus or minus 2, plus or minus 3 is a proper divisor of 15, like that. So, by using that divisibility, the simple theorem, this is a preliminary theorem you are proved in the PU level, guys. If R is a commutative ring, then A divides A is called a reflexive property. A divides B and B divides A is called a symmetric property. Suppose A divides B and B divides C, this implies A divides C. This is called a transitive relations. This you are familiar in the PU form, PUC. The same result I can use the last one as theorem. If R is a commutative ring, then A divides B and B divides C. This implies A divides C. The relation is divisibility, nor is a transitive relation. Suppose A divides B and A divides C. Simply say A divides B plus C. A divided B plus. By using the transitive relation, we add by using divisibility. Simple proof. So what's A divided B? B can be written as AK1. A divided C can be written AK2. So adding 1 and 2, B plus C is equal to AK1 plus AK2. So B plus C equal to AK1 plus AK2. B plus C is equal to A times of K1 plus K2. What's a B plus C is equal to A of K1 plus K? You can take some big K. So certainly A divides B plus C. Simple result. We can prove A plus C. Similarly, take A divides B. This implies A divides Bx. Where x is an element of R, we can solve. X is an element of R, we can solve. Using the simple, we extend this result by let R be a commutative ring with the unity element 1. The relations in R defined by A is an association of B. Is associate of B. It's an equivalence relation. What's the equivalence property? Normally at all, it's a reflexive. What's a reflexive property? A be an elements of R. Then A we can write 1 into A. A can be written as 1 into A. That is A equal to 1 into A. What means that? Therefore, A tilde A means A associate itself. A associate A. Because 1 is a unit, thus tilde is a reflexive. Now we come to the symmetry. If we have A tilde B means A equal to UB, where U is a unit element in R. Here U is a unit element in R on that. So suppose I am multiplying U inverse. What's U inverse? So 1 is the identity unit element. 1 by 1 is also unit element. Means inverse is also unit element, simply as same. So I am multiplying throughout by U inverse. U inverse into A equal to U inverse into UB. So U inverse into A, U inverse into A, U inverse into U is what? 1 into B. Generally we can write U inverse is U. U inverse identity is U inverse is U. So we can write B is equal to U inverse A. So U inverse is identity inverse is identity. Simply say unit element inverse is unit. So simply say B tilde A. This is symmetry property. So tilde is a symmetric property. Now we come to the A tilde B tilde C. What's A tilde B means? A we can write U into B. A is equal to U into B. So B tilde C means B equal to V into C. So U and V is a unit elements. So I am substituting B equal to VC. So A is equal to U of V into C. So UV of C. So U is a unit, V is a unit. Unit into unit is a unit elements. Simply say A is equal to some unit element. Simply say some PC. P is a unit. So A equal to PC. P is a unit element. Suddenly A tilde C. So this is called a transitive. Tilde is a transitive relations. This is a simple theorem. We are using a association and a divisibility. This is association theorems. So